Hello and welcome! Today, we're going to take a dive into the absolutely wild world of Albert Einstein. It's a world where everything we think we know about reality, space, time, gravity, gets turned completely upside down. We all walk around with this gut feeling for how the universe works, but a little over 100 years ago, Einstein came along and showed us that our intuition, well, it's spectacularly wrong. Okay, let's just jump right in with a simple question. Does time actually flow the same for everyone? I mean, our entire life experience screams, yes, of course it does. A minute for you is a minute for me, end of story, right? Well, according to Einstein, the answer is a hard no. And that one idea, that single thought, doesn't just bend the rules, it shatters our whole concept of a universal clock and opens the door to a reality that is way, way stranger than we ever imagined. And this really gets to the heart of it. On the left, that's the universe we feel we live in. It's neat, it's tidy, time just ticks along, space is just this fixed stage for everything to happen on, and gravity is a force, like a rope pulling things down. But on the right, that's Einstein's universe. And over there, time and space aren't separate things. They're woven together into this four-dimensional fabric called spacetime that can literally stretch and shrink and curve. And gravity? Well, it's not a force at all. It's just what we feel when we move through that curved fabric. So, how in the world did Einstein come up with all this? I mean, it sounds like science fiction. Well, it all kicked off because of a major crisis. See, back in the late 1800s, physics had these two beautiful sets of laws. One described motion, and the other described light. The only problem? They totally contradicted each other. The universe's instruction manual just wasn't adding up. For hundreds of years, everything was based on this really common-sense idea from Galileo. Picture this. You're inside a ship sailing on a perfectly smooth sea. If you drop a ball, it falls straight to your feet, just like it would if you were standing on the shore. From your point of view, the laws of motion are exactly the same. It just makes sense, right? And this principle worked for everything, from planets to cannonballs. And then came light. Light was the problem child. The laws for light and electricity, figured out by the brilliant James Clerk Maxwell, predicted something bizarre. They said the speed of light in a vacuum is always the same, a universal constant. It doesn't matter if you're standing still or racing towards a light beam at half its speed. You will always measure its speed as the exact same number. And that just completely breaks Galileo's rules. And this wasn't just some weird idea on a chalkboard. In 1887, a legendary experiment by Michelson and Morley tried to find this expected change in the speed of light as the Earth orbits the sun. They looked, and they found nothing. Zero change. The speed of light was stubbornly, maddeningly constant. So by 1900, physics was truly stuck. Two of its greatest theories were in a head-on collision. And this is where a young patent clerk named Albert Einstein walks onto the stage. Instead of trying to find a flaw in one theory or the other, he had the incredible audacity to say, what if both theories are right? What if the thing that's wrong is our basic understanding of reality? He basically proposed a reboot of physics built on just two simple, powerful ideas. And here they are. First, he said Galileo's idea was right, but it needed to be bigger. All the laws of physics, light included, are the same for anybody moving at a constant speed. Second, he just took that crazy experimental result about light and said, okay, that's not a puzzle to be solved. That's a fundamental rule of the universe. The speed of light is always constant for everyone. See the genius here? By insisting that both of these things were true, he forced a conclusion. Something else had to be flexible, and that something else was space and time itself. So if you accept those two rules, you have no choice but to accept some seriously strange consequences. If the speed of light absolutely must be the same for you on the ground and for me on a rocket ship, then our clocks and our rulers can't be absolute anymore. They have to stretch and shrink. They have to become relative, all to protect that one universal speed limit. First up is something called time dilation. Put simply, moving clocks run slow. The faster you fly through space, the slower you travel through time, compared to someone standing still. And this is not an illusion. It's not a trick of the clock. Time itself is actually passing more slowly for you. We have seen this happen. We've measured it with atomic clocks on jets, and even with tiny particles whizzing through our atmosphere. It's real. So not only does time stretch, but space itself shrinks. That same spaceship would actually look shorter to someone watching it fly by, but only in the direction it's moving. Now, if you're on the ship, everything seems perfectly normal to you. But from the outside, the universe has literally contracted space around you. Now, this might be the weirdest one of all. It completely destroys the idea of a universal now. Two things that happen at the exact same moment for me could happen at totally different times for you if you're moving relative to me. This means your present moment is just that, yours. There is no single now that everyone in the universe agrees on. Mind-blowing, right? And from all of this weirdness about space and time, you get what is easily the most famous equation in all of science. Einstein realized that if his theory was right, then mass and energy are just two different forms of the same thing. Mass is just an incredibly dense, locked-up form of energy. And the conversion rate between them? It's c squared, the speed of light times itself, which is a ridiculously huge number. And that explains the unbelievable power you get from nuclear reactions. So by 1905, special relativity was a massive success. It tied together space, time, mass, and energy. But it was still just a special case. It only worked for smooth, constant motion. It didn't say anything about acceleration, and it completely left out the biggest player in the cosmos, gravity. So Einstein knew he wasn't done. He spent the next 10 years battling this next great puzzle. So here's how you can think about the two theories. Special relativity is like the foundation. It's the rule book for a flat spacetime with no gravity. General relativity is the whole building. It's the general theory that brings gravity into the picture by saying that mass and energy literally tells spacetime how to curve. And this is the giant conceptual leap. In general relativity, gravity is not a force pulling things. No way. When you see an apple fall from a tree, it's not being pulled. It is following the straightest possible line it can through spacetime, which has been warped by the Earth's mass. The ground gets in its way, and that's what we feel as weight. You in freefall are actually following the natural, force-free path through the universe. Now, a cool theory is one thing, but does it actually work? Well, general relativity made some truly jaw-dropping predictions. It said that huge objects like the sun should literally bend the path of light, that time should tick slower the deeper you are in a gravitational field, that the entire universe had to be expanding or contracting. And guess what? Every single one of these predictions, right down to the discovery of gravitational waves just a few years ago, has been proven correct. At this point, you're probably thinking, okay, black holes, bending light, this is all fascinating stuff for astronomers, but what does it have to do with me? And the answer is, a whole lot more than you'd think. This century-old theory is humming away inside a device that is probably in your pocket right now. Just think about the GPS in your phone. The satellites orbiting Earth are moving incredibly fast, so special relativity says their clocks should tick just a little bit slower than ours. But they're also in weaker gravity, so general relativity says their clocks should tick a little bit faster. To get your location right, the system has to account for both of these effects perfectly. If it didn't, the whole GPS network would build up errors so fast, about 38 microseconds a day, that it would be completely useless in a matter of minutes. So there you have it. Einstein's theories took us from a broken physics to a unified cosmos, weaving space, time, and gravity into one beautiful picture. But it leaves us with one final huge question. We now have this incredible theory for the universe at its largest scales. And we have another incredible theory, quantum mechanics, for the world of the very small. The next great puzzle, the real holy grail of physics today, is figuring out how those two theories can finally be united.